The sheer immensity of the cosmos, a concept that strains the very limits of human cognition, begins with a surprisingly comprehensible, yet fundamentally limiting, geometric analogy: the observable universe as a colossal sphere, with our terrestrial location, Earth, positioned precisely at its geometric center. This centering is not an assertion of cosmic importance, but rather a consequence of our observational constraints. We are at the nexus of all information that has had time, since the dawn of time itself, to reach us. Inside this enormous, perceived boundary, the entirety of our cosmic senses resides: the shimmering tapestry of galaxies, the fiery crucibles of stars, and the ethereal nurseries of nebulae. Yet, to gaze upon any object within this sphere, be it the Andromeda Galaxy or the most distant quasar detectable by the James Webb Space Telescope, is not to witness it in its present state, but rather to engage in an act of cosmic time travel. The fundamental bedrock of this temporal delay is the finite, albeit staggeringly high, speed of light, often designated as the constant, c. approximately 299,792,458 meters per second in a vacuum. When we observe the Sun, that familiar celestial anchor of our solar system, we are seeing photons that departed its photosphere roughly 8 minutes prior. Extrapolating this principle across intergalactic distances reveals the true nature of astronomical observation. The telescope functions as a highly sophisticated chronoscope, painting pictures of the deep past. This temporal relationship dictates an absolute, inescapable observational horizon, one that no conceivable leap in technological prowess, no quantum entanglement communication, no theoretical warp drive, can fundamentally circumvent, because the barrier is rooted in the architecture of spacetime itself and the universal speed limit imposed by relativity. If an astronomical object's emitted light began its journey toward us at a time when the distance separating that object and Earth was greater than the distance light could traverse between the moment of emission and the present moment, those ancient photons will simply never arrive. The standard cosmological model, rooted in the Big Bang theory, posits that the temporal duration since this initial singularity event is approximately 13.8 billion years. This duration establishes a theoretical radius for our observable sphere, suggesting a boundary at 13.8 billion light-years. However, the reality of cosmic cartography is dramatically complicated by the dynamic, expansive nature of the universe itself. As light from a distant galaxy commenced its pilgrimage across the void towards our detectors, the space separating that galaxy and our nascent vantage point was continuously stretching, an effect described by the Hubble parameter, a measure of the rate of expansion. Consequently, the galaxies that emitted the oldest light we can detect today are now situated far beyond that initial 13.8 billion light-year distance, carried away by the relentless expansion of the metric of space. Current precise measurements, often derived from observations of the cosmic microwave background radiation, the faint afterglow of the universe when it was only about 380,000 years old, specifically when the epoch of recombination occurred, decoupling photons from matter, indicate that the actual physical radius of this observable sphere, the comoving distance to the surface of last scattering, stretches to an astonishing nearly 46 billion light-years in every direction. This defines our cosmological horizon, the sharp edge of the knowable. The profound question then arises, one that haunts the edges of physics and philosophy: what lies beyond this impenetrable, light-speed-determined demarcation? The honest, scientifically rigorous answer is that we do not know, and the pessimistic, yet currently accurate, projection is that we may never know. Our knowledge of physics, particularly general relativity, is built upon the data we can collect. Without any incoming photons from beyond this boundary, any statement about the nature of the unobservable remains speculation, albeit informed speculation rooted in theoretical extrapolation. Within the confines of this observable bubble, the distribution of baryonic matter, the familiar stuff of atoms, is far from uniform. Matter is not smoothly sprinkled across the volume, instead, it aggregates in a strikingly hierarchical structure, a cosmic scaffold of increasing complexity. If the universe were imagined as a colossal, three-dimensional architectural project, galaxies would serve as the foundational building blocks, the individual bricks. Current estimates, refined through deep field surveys like the Sloan Digital Sky Survey and extrapolations from higher resolution data provided by advanced instruments, suggest that within our 46 billion light-year radius observable volume, there exist approximately 2 trillion distinct galaxies. These galaxies are rarely solitary entities. The overwhelming majority exist within gravitational collectives. Galaxy clusters represent the next level of organization, collections containing anywhere from a few dozen to several thousand galaxies, bound together by mutual gravitational attraction. These clusters are not merely collections of stars and galaxies, they also contain prodigious quantities of extremely hot, tenuous intergalactic gas, predominantly ionized hydrogen and helium, which radiates energy primarily in the X-ray spectrum, key diagnostic tool for identifying and characterizing these massive structures. Beyond clusters, gravity organizes these structures further into superclusters, vast assemblages where clusters themselves are gravitationally associated, though often still in the process of virialization, the process of settling into a stable, gravitationally bound state. Our own Milky Way galaxy, an intermediate-sized spiral, is a member of the local group, a relatively small collection of about 50 galaxies, which in turn forms a peripheral part of the gargantuan Laniakea supercluster, a structure spanning hundreds of millions of light-years and containing the mass equivalent of perhaps 100,000 Milky Ways. However, the concept of largest in the universe is a fluid one, constantly being redefined by deeper observations. Even superclusters, seemingly the zenith of gravitational agglomeration, subsumed into even grander configurations. The discovery of monumental structures like the Hercules Corona Borealis Great Wall, identified through gamma-ray burst observations which act as exceptionally luminous, distant beacons, provides a chilling sense of scale. This contiguous structure of galaxies and associated matter stretches across an estimated 10 billion light-years, meaning it encompasses almost 10% of the observable universe's total diameter. This phenomenon illustrates a fundamental principle of cosmic architecture. The universe is a system nested within another system, which in turn is nested within a larger one, a pattern suggesting an almost fractal complexity, though true mathematical fractality remains debated at the very largest scales due to the finite age of the universe limiting the maximum achievable scale factor. Zooming further out from these superclusters reveals the scaffolding upon which they are built. Scientists have yet to definitively discover any structure exceeding the scale defined by cosmic filaments. These filaments are the colossal, rope-like structures composed of superclusters, associated dark matter halos, and the thin, diffuse intergalactic medium. These luminous tendrils can extend for hundreds of millions of light-years, weaving a complex cosmic mesh. Crucially, where these filaments intersect or abut, massive clusters form. Conversely, the vast regions lying between these filaments are characterized by enormous expanses almost entirely devoid of luminous matter. These are the cosmic voids, regions that can span hundreds of millions of light-years, representing the emptiest volumes in the known universe. The interplay between these dense filaments and empty voids generates the characteristic cosmic web morphology, the large-scale structure of the cosmos, strongly consistent with predictions derived from gravitational instability theory acting upon initial quantum fluctuations imprinted in the early universe, as evidenced by the highly uniform temperature fluctuations observed in the cosmic microwave background radiation maps. Earth, in this context, is not even a single atom in the web, but rather an infinitesimal mote of dust settled somewhere within one of the more densely populated nodes. This entire description, this census of galaxies, clusters, and the web structure, encompasses only the visible components of reality. This is perhaps the most jarring revelation of modern astrophysics. Everything we can directly detect through electromagnetic radiation, the stars that burn, the planets that orbit them, the nebulae that paint the darkness, accounts for a staggeringly small fraction of the universe's total mass energy budget, a mere 5%. The remaining 95% is composed of entities that evade direct scrutiny through conventional means, dark matter and dark energy. Dark matter, constituting approximately 27% of the total content, is the invisible gravitational glue that holds structures together. Its defining characteristic is its non-interaction with the electromagnetic force. It neither absorbs, reflects, nor emits photons across the entire spectrum, rendering it completely invisible to conventional telescopes. Our conviction in its existence is derived entirely from gravitational effects observed on macroscopic scales. It is the observed rotation curves of spiral galaxies, where the outer stars orbit far faster than predicted based solely on the visible mass, that first strongly implied its presence, dating back to the foundational work of astronomers like Fritz Zwicky in the 1930s concerning the Coma cluster, though Vera Rubin provided the conclusive observational evidence in the 1970s. Furthermore, the gravitational lensing effect, where massive concentrations of matter bend the path of light from background objects, provides independent, geometric confirmation of the distribution of dark matter halos surrounding galaxies and clusters. While the precise nature of the dark matter particle remains one of the most pressing unsolved problems in particle physics, leading candidates include weakly interacting massive particles, or WIMPs, hypothetical particles predicted by various extensions of the Standard Model, or lighter candidates such as actions, though increasingly, experimental data from direct detection experiments deep underground, like the LUX Zeppelin experiment, are constraining the parameter space for these traditional candidates. The remaining, even larger component, nearly 70% of the universe's total mass energy density, is dark energy. This entity is far more mysterious than dark matter. While dark matter acts gravitationally to slow expansion, dark energy exerts a uniform, repulsive pressure throughout space-time, actively driving the universe's expansion to accelerate. This discovery, made independently by two research teams in 1998 through meticulous observations of distant Type Ia supernovae, standard candles whose consistent intrinsic luminosity allows for precise distance measurement, revolutionized cosmology, earning the principal investigators the Nobel Prize in Physics in 2011. Before this, the expectation, based on the known density of matter, was that the expansion initiated by the Big Bang should be decelerating. The observation that distant supernovae were dimmer, meaning they were farther away than expected for a coasting universe, provided undeniable proof of acceleration. The leading theoretical interpretation of dark energy is its association with the cosmological constant, denoted by the Greek letter lambda, first introduced by Albert Einstein in his equations of general relativity, initially to force a static universe, a historical detour that now finds new relevance. In the modern context, the cosmological constant is often interpreted as the energy density inherent to the vacuum of space itself, vacuum energy. The problem here is one of staggering magnitude. Theoretical quantum field theory calculations of the zero-point energy of the vacuum predict a value that is about 120 orders of magnitude larger than the observed cosmological constant derived from astronomical data, a discrepancy so vast it is often termed the worst theoretical prediction in the history of physics. This profound mismatch suggests that either our understanding of gravity at cosmological scales is incomplete, or our understanding of quantum vacuum energy is fundamentally flawed, or that some unknown physical mechanism is actively cancelling out the vast majority of this predicted energy, leaving only the small residual observed today. Unlike ordinary matter and dark matter, which dilute as the universe expands because the total amount remains constant while the volume increases, the energy density of dark energy, if it is indeed the cosmological constant, remains constant. As the volume of space grows, the total amount of dark energy within it increases proportionally. This characteristic ensures that dark energy's dominance over the dynamics of the universe will only strengthen over time. If this holds true, the fate of the cosmos is sealed by this pervasive, repulsive force. The consequence of sustained, accelerating expansion driven by constant dark energy density leads toward a scenario colloquially termed the Big Freeze, or, more accurately, the heat death of the universe. As distances increase exponentially, galaxies outside our immediate gravitationally bound local group will eventually recede faster than the speed of light relative to us, meaning their photons will never reach us, effectively disappearing beyond our future cosmological horizon. Star formation will cease as gas reservoirs are depleted, existing stars will exhaust their fuel, eventually becoming white dwarfs, neutron stars, and black holes. Over timescales far exceeding the current age of the universe, trillions upon trillions of years, even these stellar remnants will decay or evaporate, leading to a universe of extreme dilution, characterized by incredibly low temperatures approaching absolute zero, a state of maximum entropy where no useful work can be extracted, cold, dark, an impossibly empty expanse. This understanding of the non-baryonic 95% shifts the very definition of universe. When we discuss the observable universe, our 46 billion light-year radius sphere, we are discussing a structure composed almost entirely of things we cannot see, whose existence is inferred only through their gravitational fingerprints or their influence on space-time dynamics. The visible matter, the stars and planets we inhabit, is merely the luminous froth atop an ocean of unseen gravitational potential and repulsive cosmic pressure. Returning to the structure within the observable volume, the Webb analogy, while compelling for describing matter distribution, requires careful consideration of scale and homogeneity. Cosmological principle, cornerstone assumption of modern cosmology, posits that on sufficiently large scales, the universe is both homogeneous, meaning it looks the same everywhere, and isotropic, meaning it looks the same in every direction. The observable evidence strongly supports this principle when one zooms out beyond scales of a few 100 million light-years. The filaments and voids, while visually dramatic, begin to smooth out when averaging the density over volumes exceeding perhaps 300 million light-years. If the universe is truly homogeneous on scales larger than the observable horizon, then the reality beyond that horizon is likely a continuation of this web structure, populated by the same ratios of dark energy, dark matter, and ordinary matter. The concept of the boundary itself invites further exploration beyond the observational horizon. Is the universe spatially finite or infinite? General relativity, coupled with observations of the curvature of spacetime derived primarily from the cosmic microwave background data collected by missions like the Planck satellite, strongly constrains the overall geometry. The critical density parameter, omega total, which describes the ratio of the universe's actual energy density to the density required to halt the expansion after infinite time, appears to be extremely close to 1. An omega total exactly equal to 1 implies a geometrically flat universe. In the context of standard cosmology, a flat universe is spatially infinite. If the universe were positively curved, like the surface of a sphere, it would be finite but unbounded. If it were negatively curved, like a saddle, it would be infinite. The high-precision measurements of the CMB anisotropy confirm a spatial flatness to within a fraction of a percent, heavily favoring an infinite or at least vastly larger than observable extent. If the universe is spatially infinite and flat, then there is no edge, no wall, no boundary beyond which space simply terminates. Instead, the pattern of matter, the very laws of physics, would continue infinitely. In such a scenario, the very concept of beyond loses meaning, as infinity has no outside. However, the discussion of boundaries often drifts into the realm of the multiverse hypothesis, a theoretical consequence arising from several lines of reasoning in contemporary physics, notably inflationary cosmology and string theory. Eternal inflation, an extension of the standard Big Bang model, suggests that inflation, the period of hyperrapid expansion in the first fraction of a second of existence, never truly stopped everywhere. Instead, it continues eternally in most regions, spawning discrete, bubble universes, each potentially governed by slightly different effective physical constants or dimensionality configurations, though still adhering to the underlying overarching physics of the larger inflationary spacetime. Our observable universe would then be just one such bubble that nucleated and stopped inflating, allowing baryonic matter to cool and form structures according to our local physics parameters. In this context, the boundary isn't a spatial edge, it is a transition between causally disconnected, possibly physically distinct, domains within a metastructure, the multiverse. Another concept tied to potential boundaries is topology. Even if the universe is geometrically flat, its global topology might not be simple. A flat space can still be finite if it is wrapped around itself, analogous to the surface of a torus, a donut shape. If the universe possesses such a non-trivial topology, looking far enough in one direction might eventually bring you back to where you started, having circumnavigated the entire cosmos. While observations searching for repeating patterns in the CMB, which would be the telltale sign of a small, wrapped universe, have yielded no definitive evidence, the finite size required for such a wrap must, at minimum, be larger than the diameter of our observable region, suggesting if it exists, it is far larger than 46 billion light-years across. The transition from the certainty of the observable to the speculation of the unobservable necessitates a constant re-evaluation of our epistemic limits. We operate based on the observable universe, which is defined not by any inherent physical barrier in space, but by a temporal barrier, the time since the Big Bang. If we wait long enough, our observable universe will grow, but only by incorporating regions that were previously too far away for their light to have reached us. Yet. However, due to the accelerating expansion driven by dark energy, a phenomenon often modeled by the equation of state parameter W for dark energy, where West is close to -1, the future observable universe will actually shrink relative to the current one. As space expands faster and faster, light emitted from galaxies currently near the edge of our horizon will eventually find its path stretched so severely by the expanding metric that those photons will never reach us, those galaxies will cross our future. cosmological event horizon, vanishing from observability forever, even if they remain physically present. This dynamic future horizon implies that the current observable universe is the largest volume of space that will ever be observable to us, making our current view a privileged, almost temporary snapshot of the totality of accessible reality. Consider the implications of this cosmic inventory: 5% luminous matter, 27% dark matter, 70% dark energy. The ratio of dark energy to matter density, omega dark energy divided by omega matter, is roughly 2 to 1 at present, a historical milestone marking the point where dark energy began to decidedly dominate the expansion dynamics over the decelerating effect of matter. This ratio determines the geometry and the ultimate fate. If dark energy was substantially weaker, the universe might recollapse in a big crunch. If dark matter dominated, expansion would slow significantly. Because dark energy is winning, the trajectory is toward ultimate cold isolation. The interplay between structure formation and these constituents is crucial. Dark matter provided the initial gravitational scaffolding. In the very early universe, quantum fluctuations created slight density variations. Dark matter, being collisionless and unaffected by radiation pressure in the early plasma, began collapsing gravitationally much earlier and more efficiently than baryonic matter. It formed halos, dense clumps that served as gravitational wells. As the universe cooled sufficiently for atoms to form, recombination, baryonic matter, now free from the intense radiation pressure, fell into these pre-existing dark matter potential wells, allowing galaxies and clusters to form where they are observed today. Without dark matter, the observed level of cosmic structure, the abundance and clustering of galaxies, simply could not have formed within the available 13.8 billion years. The simulations of structure formation, such as the Millennium Simulation, which model the gravitational evolution of billions of particles representing dark matter and baryons over cosmic time, reproduce the observed large-scale web structure with remarkable fidelity, validating the Lambda-Cold dark matter model, or Lambda CDM, which uses precisely these ratios, a flat geometry driven by a cosmological constant, dominated by cold dark matter with 5% baryonic content. The sheer dominance of the non-baryonic components underscores a profound humility in our cosmological understanding. We are, perhaps, only capable of perceiving the minor byproducts of a vastly more powerful, unseen reality. Our physics describes the interaction of the 5% with exquisite detail, from the fusion processes within stars to the chemistry of life, yet this entire edifice of classical physics and chemistry rests upon a foundation that is, for the most part, compositionally unknown. The continued search for the nature of dark matter and dark energy drives cutting-edge experimental physics. Direct detection experiments seek the faint recoil signature when a hypothesized dark matter particle, passing harmlessly through Earth constantly, happens to strike an atomic nucleus in a highly shielded detector. Indirect detection experiments look for the annihilation products, gamma rays or antimatter, that might result when two dark matter particles collide in regions of high density, such as the galactic center. Meanwhile, future space-based observatories are planned to map the expansion history with even greater precision, aiming to detect subtle variations in the dark energy equation of state parameter W over cosmic time, searching for evidence that dark energy is not the static cosmological constant but rather a dynamic field, sometimes called quintessence, which would alter the long-term cosmic fate. If W were found to be less than -1, for example, it would imply a phantom energy scenario, leading to a catastrophic Big Rip where the repulsive force accelerates so violently that it overcomes gravitational binding, then electromagnetic forces, tearing apart galaxies, stars, planets, and eventually atoms themselves in a finite amount of time. Current data strongly favors W equals -1, pointing to the Big Freeze, but the precision required to rule out subtle variations remains a formidable challenge. Contemplating the boundary of the universe inevitably leads us to the boundary of time itself. The initial singularity, the Big Bang, represents a boundary in the past, a moment before which, under the Standard Model, our current understanding of spacetime breaks down. The question of what caused the Big Bang, or what preceded it, ventures into realms where time itself, as defined by the expansion of the universe, loses meaning. Some speculative models propose cyclical cosmologies, where the Big Bang is merely a transition point, a big bounce, following the collapse of a previous universe. These models attempt to circumvent the singularity problem by introducing mechanisms that halt gravitational collapse and trigger a new expansion phase, often relying on exotic physics or modified gravity theories. The entire framework, from the 5% of visible stuff to the 95% of invisible drivers, is encapsulated within the observable sphere of 46 billion light-years radius. This sphere is the extent of our causal horizon, the region from which events can influence us, or from which we can receive influence. If the universe beyond is indeed infinite, then every possible configuration of matter must statistically occur somewhere, and infinitely far away, leading to the ultimate, perhaps unsettling, implication of cosmological repetition. There are infinitely many other observable universes, separated by vast, expanding gulfs of space, that are essentially duplicates of our own, perhaps even containing copies of you reading this sentence. The ongoing quest to understand the universe's size and boundary is therefore not merely an exercise in astronomical measurement, it is a test of the fundamental completeness of our physical theories. Are gravity and quantum mechanics destined to remain unreconciled at the highest energy regimes that defined the early moments and the very structure of the cosmos? Does the ultimate fate lie in the cold drift of the Big Freeze, or is there some unknown physics, perhaps associated with the nature of the vacuum itself, that will yet reshape the cosmos? We observe the past, constrained by the speed of light, within a structure whose visible components are a mere trace element of its total content, all while standing at the center of a sphere whose true, total extent remains either infinitely large or permanently hidden behind the accelerating veil of dark energy. The universe is vast, defined by what we see, but its true scale is dwarfed by the shadow cast by what we cannot see, shadow quantified as 95% of all that is.